So first we're going to look at series circuits. And series circuits are where all of your objects, so say we have little light bulbs here, all of the lights are in series with each other or along one single path. They're all in a row. One challenge of a series circuit, and you might have had this experience with Christmas lights, is if any one of the lights blows out, right? So you get a broken bulb, then the whole circuit will stop working. Basically, current will stop flowing, right? That creates a break in the circuit, and we know that current can only flow in a closed loop. So if any one of the light bulbs goes out, we no longer have a closed loop here. We have a break, so no current will flow. And all the lights are dark. So it makes it really annoying with a Christmas light circuit. If one of your light bulbs blows out, then you can't figure out which one is the broken one because all of them go dark. So you have to carefully look at each light bulb and try and notice which one has the broken filament in it. And it's really hard to spot if you have Christmas lights that happen to be in a series circuit. So that's kind of what a series circuit is. It's closed loop, but just one path for the electricity to go, and all of your elements, so those are little lamps or whatever they are all in a row. All right, so here's 3 different circuits. So here's just the simplest possible circuit you could have. We've got a battery, a 6-volt battery connected to a single little Christmas light here. We were actually going to do this in class. It was going to be really fun. We're going to build these. Here's another battery connected to 2 little Christmas lights in series. And here's another battery, same battery, connected to 3 Christmas lights, all in series. So which one of these circuits would have the most total resistance? Like if we add up the whole resistance of the whole circuit, which one would have the most? Hopefully intuitively, you're thinking it's probably circuit C, and that would be true. The reason why it's circuit C is that in series, resistance adds. So this is because in series, resistance adds. So that means as you add more light bulbs in series, you add more and more resistance. And that kind of makes sense. All the electrons have to go through every bulb. So if you add more bulbs for them to go through, each light bulb is another resistor. It causes more resistance. So you have to go through this resistor and this resistor and that resistor. That's going to be harder than if you just have to go through one. All the electrons, or I guess I could say all the current, must go through every bulb. And so just adding more bulbs means more resistance. It's kind of intuitive that way. Adding more bulbs is more resistance. Well, then which one of these circuits would draw the most current out of the battery? So think about that for a second. What do you think? Hopefully you're thinking it would be A, because it would be. We know that current, this is Ohm's law, that super famous law, it's delta V over R. More voltage or more potential difference will mean more current, but more resistance means less current. That's dividing by resistance, right? And that kind of makes sense. If you have more resistance, more stuff slowing you down, you're not going to be able to pull as much current out of the battery. It's just going to be harder for the current to flow. So if you have more resistance, and that's in circuit C here, means it's like it's harder for current to flow. And so circuit A, with the least amount of resistance, is going to draw the most current. So the circuit with the least resistance, and you've probably heard of like the path of least resistance, right? that will pull the most current. All right. So just to sum that up with a formula, so in a series circuit, resistance adds. That means that as you add resistors, your total resistance will literally just add up. It's a really nice formula. The total resistance of your circuit is just going to be the resistance of the first bulb plus the resistance of the next one plus the resistance of the third one. If you have a whole bunch of light bulbs in series, you just get to add up all the resistors, the resistance of each one, and that gives you the total resistance of your circuit. So if I have a circuit like this, it's a little light bulb here, a light bulb here, one more over here, comes back. This one is say like 3 ohms and 4 ohms and 1 ohm. My R total would be just add those up, 3 plus 4 plus 1. So the total resistance of that circuit is going to be 8 ohms. Okay, just add up all those light bulbs in series. An analogy I think can be helpful. Maybe this one seems so simple and so intuitive that maybe you don't need the analogy, but it becomes really handy when we talk about parallel circuits, which are a little less intuitive. So we're going to use the same analogy for both. So let's say you're trying to move a current of cars. So our analogy for current here is going to be like the number of cars that pass a point per second from Kingston to Oakville. And then there's multiple locations along the road. So you're going down maybe the Highway 401 where you're reduced to 1 lane because of construction. So each additional construction zone is going to add resistance to the flow of traffic, right? So the more construction zones, you go through, the more your traffic gets slowed down, the harder it is to push cars down the highway, which means that more construction zones decreases the current of cars. So that's how it works in a circuit. As you add more resistors in series, so more construction zones, everyone you go through adds more resistance. That's going to decrease the current of cars that can actually go down the highway. The last thing I want to look at is potential difference. And potential difference, our analogy of height is going to be really, really helpful here. So when you go through a battery, you gain some energy. Every electron gets a little bit more energy. That's kind of what the potential difference is how much electrical energy each little coulomb of charge is carrying with it. But that's a really abstract way to think about it. I think height helps a lot. So think about it as when you go through a battery, you're gaining some 6 volts of height. So you like go up a 6-volt high mountain here when you go through the battery. And then you go along the circuit, and as long as you're going through a wire, you don't lose your height because your wire doesn't have much resistance to it at all. So we just go along here. But then we get to the first light bulb. And the first light bulb has some resistance. So we're going to have to use up some of our energy to make it through that light bulb. And when we use up energy, we're literally like dropping down in height. So maybe if there's 2 bulbs in series, maybe the first bulb uses 3 volts of energy, and then the second bulb uses another 3 volts of energy. But the key is that by the time you get back to the battery in our closed loop, because circuits always have to be in a closed loop, we have to have used up all of the height that you gained at the battery so that we can go up again. Otherwise, like this wouldn't be a closed loop if we didn't use up all of our height. So let's imagine a different scenario. What if instead of using 3 volts at this first light bulb, maybe you use 4 volts? Well, then that would mean the second light bulb would have to use 2 volts, right? So that we get back down to 0. So if we go up 6 volts with the battery, we drop 4 volts in height here, well then I would have to drop 2 volts in height here to get back to the battery. So the light bulbs don't actually have to use the same amount of energy. The key is just that all of that height has to be gone by the time you've returned back to the battery in a closed loop. How it actually works is that the light bulb with the greater resistance will use up more energy to go through it. So you'll have a bigger voltage drop with the greater resistance light bulb, which kind of makes sense. It has more resistance, it's harder to get through, so you have to use up more energy to go through that bulb. So it kind of all works together. Right, so then in these 3 circuits here, let's erase this and go back to what we actually have here. So in these 3 circuits, which one would have the biggest potential drop across a single light bulb in it. So think about it for a second. And hopefully you said A. Let's actually figure out the potential drop across each one. So in circuit A, you gain 6 volts at the battery. You have to use up that entire height by the time you get back to the battery. But there's only one light bulb to use up your height. So you have to drop 6 volts at that light bulb. You have to use all 6 volts. In circuit B, you gain 6 volts at the battery, so you gain 6 volts of height. But that's actually this situation right here. If these two light bulbs are each identical, then you'll use 3 volts at the first and 3 volts at the second. So you use up 3 volts, use up another 3 volts, and you're back down to the ground level for you to go through the battery again. And for circuit C, if you gain 6 volts at the battery, you're going to lose 2 volts at the first light bulb, 2 volts at the next, 2 volts at the last. Now, do remember that they don't always have to be shared equally like this. I'm just sharing them equally because in this case, these are all identical Christmas lights, so they would all be identical. But they don't have to be, if they're not identical lights, then some of them would use up more voltage than others. But that means clearly that the largest potential drop across a single light bulb will be in circuit A. So that is because when you complete a closed loop, around the circuit, you need to use up all of the voltage you gain at the battery. All the voltage or all the potential difference gained at the battery. And of course, in circuit A, there's only one light bulb that to go through, so you have to use up all 6 volts there.